Hello everyone, this is Jose Campos Salazar, and today I will present a research and engineering study titled as Modeling and Control of the X-Filter for Enhanced Pulp Mill Performance. This presentation is going to be an attempt to present our work on modeling and controlling the X-Filter located in any coautizing plant. The goal is to understand the process dynamics and evaluate how model predictive control can improve stability, robustness, and operational performance compared to traditional proportional integral control. I'll begin with the process description and motivation, followed by modeling, control designs, and simulations results. The presentation begins with the motivation and process background, followed by a detailed description and dynamic modeling on the X-filter. I will then introduce the control strategy, focusing on proportional integral and MPC, before discussing simulation results and concluding with key insights and future perspectives. The pulp and paper industry is a highly energy and resource intensive sector, where process efficiency has a direct impact on operational cost, product quality, and environmental performance. Within kraft pulp mill filtration, this machine play a critical role, particularly in the clarification of green liquor between the recovery boiler and the coautizing plant. As modern mills operate under tight environmental and production constraints, the accumulation of non-process elements such as magnesium from oxygen delignification plant has increasingly degraded traditional settling and filtration performance. But okay, what is the X-filter? X-filter is a cross-flow film forming filter designed to address these challenges by enabling continuous solid-liquid separation while reducing filter fouling. But however, of that, its operation involves strong multivariable coupling, nonlinear dynamics, and sensitivity to disturbances, which limits the effectiveness of conventional PI control strategies. So, in this work, we present the first comprehensive dynamic model of this X-filter and investigate the application of model predictive control to improve its operation. Through detailed simulation, we demonstrate that MPC significantly enhanced dynamic response, disturbance rejection, and robustness compared to classical PI control. With this motivation in mind, the next section introduces the X-filter process and its dynamic modeling framework. The X-filter process consists of two main units: the X-filter itself and downstream storage tank. As you can see here in figure 2. Figure 2 is a reduced process diagram regarding this machine. Now, the X-filter includes a pressurized vessel, two filter cloth elements, an internal vessel where filtered green liquor accumulates. Raw green liquor is pumped into the system through both bottom and top inlet. Okay. Now, the bottom inlet floods the filter upward, while the upper inlet feeds the internal vessel. Now, from here, basically, the liquid flows through conduction channels toward the filter cloth. But also filtration is driven by a controlled pressure difference between X-filter vessel and internal vessel. All this you can see in figure 2. Now, compressed air pressurizes the system and directly influences the filtration capacity. But also, filtered liquid is collected into the internal vessel and routed to the storage tank, while vapor and air are discharged through a dedicated outlet, as you can see again in the figure 2. Finally, the storage tank acts as a buffer regulating the final outlet flow. The process relies on the loss flow cross flow filtration, where downward liquid motion continuously cleans the filter surface, preventing particle adhesion and ensuring stable operations. The key state variables of this system are the following: liquid levels, designated as H1 and H2, and the effective filter height, which is defined by the equation shown here. Now, but based on this process configuration and flow structure, dynamic model is now derived to capture the coupled hydraulic and pneumatic behavior of this X filter. Now, in this section, we try to develop a complete dynamic model of this machine. The goal is to capture the essential nonlinear dynamics and then derive linear and S-domain models suitable for controlled design. But although the full X-filter operates across multiple stages, this study focuses specifically on the pumping and filtration dynamics, which are the dominant contributors to system behavior and control interactions. The X-filter process consists of multiple operation stages, but in this time, only the pumping and filtration stage are modeled. These stages dominate the hydraulic and pneumatic dynamic relevant to control. Two control volumes are defined: the X filter itself and the downstream storage tank, as we talked before, right? In addition to process modeling, the system offers suitability potential, as green liquid dregs contain calcium carbonate that can be reused in ceramic application, for instance, but not in this case. In this case, it's just an output, but it's not of interest in this study. Now, nonlinear model starts with fundamental conservation law, as maybe you know. A mass balance of the X-filter yields the dynamics equation for the liquid level, as you can see in this slide. Vapor dynamics or gas dynamics are described through a molar balance, and because operating pressures are low, the ideal gas law is used to relate vapor moles to pressure in order to get an coupled dynamic equation. Now, substituting this relation results in a pressure dynamic operations based on the equation for the especially located in the intervessel, which directly links air injection and vapor discharge to the system pressure. Now, the filtration dynamics are modeled through a cake resistant formulation, where the growth of the solid layer depends, as you know, on pressure difference, fluid viscosity, and filter properties. The factor of 2 reflects the presence of dual filter element. Maybe you know, but you should to take account that this filter got 2 filter elements. Okay. Now, a mass balance on the storage tank completes the nonlinear model, linking outlet flows to the downstream liquid level. To enable controller design, the nonlinear model is linearized around the steady state operating point because we are using a classical control theory, which is based on linear models. These points are obtained by enforcing equilibrium condition on the state derivative. So we just zero in those derivatives factors. A Taylor series expansion yields a linear state space model that preserves the multi-variable coupling of the original system, as you can see in the state dynamical equation here. The final modeling step is transforming the linearized state space model into the Laplace domain. This yields a complete multivariable transfer function matrix describing the relationship between all input and output. This representation is essential for classical control analysis and forms the predictive model used by the MPC. With this multivariable dynamic model established, the next section focuses on the design of PI and MPC controllers to regulate the X-filter process. Here we introduce the control strategy developed in this work. Two approaches are synthesized, widely used in industry. For instance, a classical PI based architecture widely used in industry, and a model predictive control strategy. The control design focuses on the variables that directly impact X-filter operation, the liquid levels and the pressure differential. The effective filter cake hides the intentionally excluded, as in industrial operation is typically handled by rebase strategies rather than active feedback control. As you can see here in figure 8, we are showing a control diagram for this process. And to design effective controllers, it was first necessary to identify the fundamental control loops of the X-filter. This loop naturally emerged from the process physics. One for the X-filter level, one for the downstream storage tank, and one governing the pressure differential that drives filtration performance. All this you can see in figure 8. So let's now look at how each of these loops was designed. The first loop controls the liquid level inside the X-filter. The identifier plan exhibits pure integrity behavior, which is common in level system. Given this structure, the direct synthesis method was selected to provide a straightforward and robust way to design PI controller with predictable closed-loop dynamics. Now, by enforcing a first-order closed-loop response, the PI parameters are analytically obtained. The integral action ensures zero steady-state error, as maybe you know, while the proportional gain shapes, the transient gain and shape the transient behavior, basically. Those results in a well-behaved and industrially realistic level control loop. Now, the second control loop regulates the storage tank level. Unlike the previous case, this plan exhibits a first-order inverse response. So, the DSM of direct synthesis method is again employed to appropriate sign compensation to maintain closed-loop stability. Now, these controller parameters ensure stable and robust operation even in the presence of inverse process behavior. Proper timing of this response time allows flexibility depending on operational requirements. The pressure difference driving filtration is regulated indirectly by controlling the internal vessel pressure for sure. So this structure avoids direct manipulation and pressure differential and aligns with industrial practices. While now PI controller offers simplicity, they struggle with strong interaction. Also, they can be affected by constraint and disturbance are present. So this motivates the adoption of MPC, for instance, which inherently addresses these challenges. Now, let's now briefly review how MPC is implemented in this work. The MPC implementation is based directly on the linearized state space model of the X-filter gathered before. And this ensures consistency between modeling, PI design, and predictive control. The strategy is shown here in figure 9. Now, the MPC architecture is shown here, and the state space model in a discretized way is shown in this equation here. Also, and this model can handle multiple input and output and measure disturbances, as you can see by the equations. Um, at each sampling instant, MPC solves an optimization problem that balances tracking accuracy and control effort. Only the first control action is applied, enable real-time adaptations, as you can see here in this equation here. Now, here um, in the following, we try to summarize how MPC is embedded into the X-filter control structure, replacing decentralized PI loops with coordinated multivariable optimization. In summary, both control strategies are valid, but MPC clearly demonstrates superior performance for this complex filtration process. This work establishes a solid proof of concept to future industrial implementation. With the process dynamic and control structure defined, we now move to simulation result where PI and MPC strategies are embedded with disturbances, noise, and multivariable interaction. Uh, the simulation environment is based on linearized multivariable model of the exit derived in the equation shown before. And this equation is implemented in MATLAB-Simulink. All model parameters were obtained from the analytical deviations presented earlier and are summarized in table 1, which is present now. While the disturbances are listed in table 2. Now, to realistic assess robustness, high frequency noise model as additive with white Gaussian noise in per unit was injected. Okay, mechanical vibration and external process perturbation typically observed in this kind of pulp mill. Now, the high frequency disturbances are mathematically represented as a superposition of sinusoidal component, as you can see here, um, uh, with a different amplitudes, frequencies, and phases. This formulation allows the simulation of broadband industrial noise with strong high frequency contents. These disturbances were intentionally designed to challenge both PI and MPC controllers and to evaluate their ability to suppress oscillatory behavior under realistic industrial operating conditions. Now, all simulations start from a well-defined stationary operating point representative of normal mill operations. Liquid levels are initialized at 50% pressure differential at minus 10 kilopascals, and valve and pump position corresponds to realistic operating values observed in industrial environments. This ensures that all transient responses are evaluated around to physically meaningful operating regime. Now, figure 10 and 11, as you can see here, reveal a fundamental difference in how the controller responds to high frequency disturbances. While both PI and MPC are exposed to noise, the MPC significantly attenuate high frequency oscillations. These behaviors emerge naturally from its predictive and optimized base structure, which smooth control action over the prediction horizons. In contrast, the PI controller directly propagates noise into the manipulated variables, producing undesirable oscillatory behavior, as you can see in those figures. Noise suppression's performance is quantified using a noise mitigation efficiency metric, defined as the relative relation in standard deviation between PI and MPC control. The result shows a 9% reduction for the upper level, 24% for the outlet time level, and 32% for pressure differential. These values clearly demonstrate the superior ability to MPC to suppress high frequency variability in critical process variables. But also, transient tests further highlight the dynamic superiority of MPC when the upper level is disturbed at 40 seconds. MPC reach steady state more than 11 seconds faster than PI. Similar improvements are observed for pressure differential and outlet level disturbances. Most importantly, oscillations are drastically reduced under MPC, confirming its effectiveness in managing multivariable interaction and disturbances. Um, um, so basically, MPC show a clearly superiority behavior against to PI behavior, basically. Now, a really important observation emerged when analyzing manipulatable variables. Under PI control, high-frequency noise couples directly into pump speed and valve positions, producing a persistent oscillation that can damage a hydraulic equipment, which is a often phenomenal where you can find in this kind of plant. Now, under MPC control, these oscillations are eliminated, resulting in a smooth control trajectories. This low-pass filtering behavior has direct implications for equipment, longevity, and maintenance cost. Additionally, disturbance tests were performed on pressure and airflow to evaluate robustness. The MPC consistently maintained stable operation with reduced variability across the controlled variable. Probability density function on the standard deviation further confirmed substantial substantial reductions in variability, reinforcing the robustness of MPC under realistic industrial disturbances. In summary, the simulation results demonstrate that MPC significantly outperforms PI control in terms of speed, stability, noise suppression, and actuator protection, making it a highly suitable control strategy for complex filtration processes such as the X filter. With this simulation result establishing the dynamic and robustness advantage of MPC over PI control, we can now summarize the key conclusion and implication of this work. To conclude, this work presents the first dynamic modeling and MPC-based control study of the X-filter process. The results clearly show that MPC outperforms traditional PI control in terms of speed, stability, and robustness, especially under high-frequency disturbances. Beyond improved control performance, MPC reduces actuator stress and enhances process reliability. Although this study is a proof of concept, it establishes a good foundation for future real-time implementation and industrial validation in pulp mill environments. That's all, and thank you for attending this presentation.